Let's begin by asking what it really means for a sequence to converge to a limit. In plain words, a sequence converges to a limit called L if for every positive tolerance we choose, no matter how small, there comes a point in the sequence after which every single term stays within that tolerance of L. We call that small positive tolerance epsilon, and we call the point after which the terms settle down capital N. So the full statement is this: for every positive epsilon there exists a whole number n, such that for every term index n greater than n, the distance between the term and L is less than epsilon. Picture this on a number line. We draw a narrow band around L of width epsilon on each side, and we watch the terms of the sequence march along. For a convergent sequence, like 1 divided by n, once we pass some point n, every later term falls inside that band and never leaves it again, no matter how tiny we make the band. Now let us test this idea with a tricky example. Consider the sequence that goes 1, -1, 1, -1, and so on forever, alternating between 1 and -1. This sequence is bounded because every term sits between -1 and 1, but we will show it has no limit at all. Picture the terms as points jumping back and forth on the number line, landing on 1, then -1, then 1 again, forever, never settling anywhere. Let us try the first principles approach. Suppose, for contradiction, that some number L is the limit of this sequence. Choose the tolerance epsilon equal to 1/2. By the definition, eventually every term must lie within 1/2 of L. But the terms only ever take two values, 1 and -1, and the distance between 1 and -1 is 2. A band of width 1/2 on each side of L only spans a total width of 1, so it is too narrow to contain both 1 and -1 at the same time. This means no matter what L we picked, we cannot keep both the even terms and the odd terms within 1/2 of L after any point n. That is a contradiction, so no such L exists, and the sequence has no limit. As a check, try any candidate L yourself. Say L equals 0. The terms 1 and -1 are each exactly 1 unit away from 0, which is already bigger than our tolerance of 1/2, confirming the contradiction holds. Now let us look at a genuinely different way to reach the same conclusion, using subsequences instead of a direct epsilon argument. Look at the even numbered terms of the sequence. They are all equal to 1, so that subsequence converges to 1. Now look at the odd numbered terms. They are all equal to -1, so that subsequence converges to -1. There is a theorem that says if a sequence converges to some limit L, then every subsequence must also converge to that same limit L. Here the two subsequences converge to different limits, 1 and -1, so the original sequence cannot converge to any single limit. This second route is genuinely different from the first because it leans on the uniqueness of subsequence limits, rather than directly hunting for a contradiction with the epsilon and n definition. So we have shown in two different ways that this alternating sequence is bounded yet fails to converge, which proves that being bounded alone is not enough to guarantee a limit exists.